Welcome to the COVID-19 online learning module for the Doppler effect. This is a unique challenge inasmuch as the Doppler effect is best observed around vehicles outside, and we are all stuck inside with no cars on the streets. So let's have some virtual cars drive by and we'll listen for the Doppler effect in action. Here's car number one. Ask yourself, what is it doing? Even though you can't see it and you can't feel the wind from it. Shall we play that again? All right, decide what that car was doing. Write down your hypothesis. When you're ready, press play. Here's car number two. What's car number two doing? Are you sure? Is it doing anything different than car number one? You can try it again. What is that car doing? All right, now write down your observations. Write down without using the words near and far. Without using the words loud or soft. And everybody has to use the word moving. I'll say that again. Everybody has to use the word moving. Write down what each car was doing without using the word loud and soft, without using the word near or far, and using the word moving in every step. All right, let's get the distractions out of the way first. If the car is near to you, we know this. It sounds loud. That's not the Doppler effect. That's common sense. Similarly, if the car is far away from you, it sounds soft. We knew that too. We didn't need to go to physics class to know that. What we're talking about here is the volume of the sound. That is to say, how loud and soft it is. That's not the Doppler effect. That's simply proximity, near and far. The car number two, that's the one that was just sitting there. You knew it was just sitting there. You knew it was idling. It was hanging out at the stoplight, waiting for you to go, honking like a New York second. Car number one, however, had something different. Car number one started with a very high pitch. And then it went meow, that characteristic race car sound. All of a sudden, it went to a very low pitch indeed. The variable that's affected here is not volume, it's frequency. High frequency, meh. Medium frequency, meh. Low frequency, meow. And just about everybody agrees when you stop to listen that this car is passing you. First, it's moving towards you. Then it passes you. Then it drives away from you. Look at the matchup. The pitch changes from high to low because the direction changed meow, from moving towards you to moving away from you. The Doppler effect is an effect that describes motion. It doesn't describe location. You don't need fancy language. You don't need a law of physics to describe location. There it is. It's near. It's really loud. It's far away. It's really soft. The Doppler effect describes how a wave changes if it sorts its moving. And the first thing that we observe that changes is the frequency. The frequency of an object moving toward you sounds higher. The frequency of an object moving away from you sounds lower. In the rest of this lab, we're going to investigate whether this is true for every kind of wave or just sound waves, and whether it has its own world and is completely absolute, or whether it's relative to you and what you're doing. Now that you know what to look for, watch the Family Adventures clip. This family is allowed to go farther than around the block, but they are out there recording physics for the rest of us. Listen to the change in pitch as the car drives by and see if the same experiment works the same way for the kid inside the car with the video camera. Next, think about where you can hear the Doppler effect in your own life. Find a sound clip. Look on YouTube for race cars, Indy 500, roller coasters, fire trucks, emergency vehicles. Look for them in conjunction with the word Doppler effect. Then try to replicate it yourself. Toss something making noise from one sibling to another. If it doesn't seem to be working so well, if you're having trouble getting a pitch change that's good enough for you to hear, there may be a reason for that, and that reason you'll explain. You may only get a small change depending on how you throw your cell phone. You won't get a big change like you'd get with a fire engine going to an emergency, a roller coaster zooming by you, or Blue Devils doing tricks over Lincoln Park and the air and water show day where the rest of us have to make sure not to be on the north side at all because we'll get our ears blown off. Pause this video. Watch the others, take your notes, make your observations, and when you're absolutely ready, press play to check your work. Ready? No, seriously, pause this video and watch the other ones. Make observations, take notes. It won't make any sense if you don't actually hear it yourself. All right, you ready? You got something written down? All right. The change, that is whether Doppler effect is really dramatic and easy to hear, or it's barely there at all and you kind of have to, physics, is speed. Fire engines and emergency vehicles go faster than the rest of us because they have to get there in a hurry and fix the emergency. You are not throwing your cell phone that fast because you don't want to break it. The reason we hear this for cars more so than for bicyclists, even though bicyclists have horns too, is that cars are going faster, and a roller coaster is going faster than the go-kart with the park employees in it, so you hear the Doppler effect much more dramatically. Big change means high speed. Small change means less high speed. It means a low speed. Now, when you're ready, watch the animated clip here and look at the wavelengths. See what happens. If this isn't making all the sense in the world, you can also look on YouTube for demonstrations of the Doppler effect on slinkies, or try it yourself at home when you have it. See how the wavelengths bunch up on one end and how they stretch out on the other hand as whatever it is that's making the wave, be it the vehicle that's making noise or the star that's emitting light, moves away. If it works for generic wave, it's going to work for other waves that aren't just sound waves. It's going to work for mechanical waves. It's going to work for light. Now, you can't use the class radar gun in class. Spoilers, it doesn't give very good data because it's designed for cars. Cars move faster than we do. But use this to review if the car is moving fast, if the car is moving slow, what should the radar frequency be? If the car is moving towards, if the car is moving away, what should the new frequency be? Fill those in the chart. When you're done with your wavelengths, again, pause now, watch the other video, take lots of notes, press play to check your work. All right, ready? Did you do your own work? Okay. If the car is moving towards you, the new radar frequency will be higher than the old. If the car is moving away from you, the new radar frequency will be lower than the old. So if the police officer is sitting there in the bushes, in the church parking lot, or Beth Shalom on Walters, they're very non-judgmental about this, and they shoot the radar at the car, one way or another, they're going to get a change. The new radar frequency that bounces off the metal back or front of the car and returns to the radar receiver on the police officer's dashboard is going to be changed. Unless, of course, the police officer misses and hits a tree when the tree is neither moving towards nor away from the car, and the car is not moving towards or away from the tree, in which case the change will be 0 and the radar frequency will come back the same as it was before. But if the car is moving towards, there will be a change. If the car is moving away, there will be a change. A small change must come from a small speed. A big change must come from a large speed, a big speed. Cops have 3 things on the dashboard. Yeah, I know they're in one kit, but they're 3 separate articles. One of them is the radar gun that sends out the waves. One is the radar receiver that receives the reflected rays back. Radar, guys, is radio waves. The third is a computer microchip that does the math on the formula for the Doppler effect and calculates how fast that car must have been going to deliver as big a change as that. Frankly, it's a very small change, the car is probably okay. If it's a very big change, the car is speeding, and the computer chip is hooked up to a little red LED, and the red LED will flash after the cop has programmed in whatever the speed limit is for that street, and if the change exceeds that speed limit, it'll flash and the police officer can turn on the siren and give chase. Again, pause here, do your work. Fill in the chart and do the Doppler effect for light. Watch the Spaceballs clip. In addition to being an epically funny send-up of Star Wars, the physics in this movie is absolutely dead on, and I have never seen a better demonstration of redshift than the one in this movie. Please note that for the Doppler effect for light, like for sound, is more dramatic depending on how fast you're going. And that means we're not going to really see the Doppler effect for light unless we're going a respectable fraction of the speed of light. Otherwise, we're just going too slowly and we won't notice it. Well, Spaceball 1 can travel at ludicrous speed, and they're going to see the Doppler effect for light as Spaceball 1 overshoots our heroes by a week and a half. So again, pause, press play to check your work. Well, for the third time, this is the Doppler effect. If the star or the spaceship is moving towards you, the wavelengths are going to be bunched up, the light will have a higher frequency. If it's moving away from you, the wavelengths will be spread apart, it will have a lower frequency. A slow speed is going to be a small change, not very visible. A fast speed, that is fast compared to the speed of light, will be a large change that will be readily visible to our eyes and our equipment. Now, look up on your electromagnetic spectrum what the higher frequency and lower frequency colors are. Press pause, look it up, write it down, and then press play to check your work. This is why we call it red. Redshift. Redshift is when the light looks redder than it should have. Look at the plaid clip in Spaceballs. Spaceball 1 has gone to plaid. Those tail lights are bluish white, but the light that the Spaceball 1 is bathed in is yellow and orange and red. It is red shifted away from the cool colors and into the warm colors, into the lower frequency edge of the spectrum. Now, by all rights, up here, this ought to be violet shift, but our eyes see very poorly in the violet spectrum, so it's generally called blue shift. Blue shift is very rare unless you have some weird interstellar wuss name that's actually moving closer to the Earth. If you look in all directions with the most advanced radio telescope, you will see redshift everywhere. Every galaxy you look at, every pulsar, every quasar, they're all redshifted. Pause and explain how redshift proves that the universe is expanding. Press play to check your work. Ready? It's a simple geometry problem. If they're all moving away from us, either we have the world's worst BO problem and nobody's told the planet yet, or it's nothing personal. They're moving away from us, we're moving away from them. The only solution to the geometry problem is that the entire universe is expanding. This is our fast and hard data that proves that infinity now is bigger than infinity used to be, and that is still bigger than infinity was at the dawn of time. It's crazy, isn't it? But think about it. How many numbers are there between 1 and 2? Like decimals and everything. It's an infinite number, right? You can cut something into small pieces an infinite number of times in math. Okay, how many numbers are there between 0 and 2? Well, it's still infinite, right? But that infinity is twice as big as the infinity between 1 and 2. Yes, you can have infinities of different sizes. You can have big infinities, you can have small infinities. The Big Bang made space. That space was infinite, but it was a small infinity that's been getting bigger and bigger as time progresses and the universe expands. Pretty cool, huh? Page.